Professor Tubaldi is a faculty in the mechanical engineering department, and she's going to be talking about how to harness mechanical instabilities for robotics applications. So please take it away. I think you're muted, so you might want to unmute yourself. And oh.
My apologies. Can you hear me?
Yes.
Everybody see my screen?
We can see your screen.
Awesome. Okay, thank you, everyone. Sorry about that. So yeah, good morning, everyone. Thank you for being here, and thank you to organizers really for organizing this wonderful event. So today I would like to talk to you about how we can harness mechanical instabilities for robotics applications. So you might be wondering where this idea comes from, right? The answer is pretty simple. So it comes straight from nature. So nature has shown us in multiple ways in the animal kingdom and in the plant kingdom how fast actuation, or more in general, high-speed motion, can be generated through mechanical instabilities. So here what you're seeing is a Vibrio engine Analyticus that is able to perform a 90-degree turn in a fraction of a second. And this is enabled by a buckling instability in the flagellar hook. And this type of mechanism, so this type of instabilities happen in nature across scales. So here, for instance, we're seeing a very hungry Venice flytrap that is using the snap-through mechanism in order to catch its prey. So you would agree with me that these instabilities are really fascinating. Now, they've not been harnessed too much in the robotic fields because they are usually associated with the idea of failure, or at least the onset of failure. So now our question is, which kind of devices we can create that can sustain structural phase transition? So researchers recently have shown that in the field of soft robotics, buckling instability can be harnessed to a soft machine that's walking, and also buckling instability has been used in the kerigami skin in order to break the symmetry and allow the soft crawlers to actually crawl and advance. For fast type of motion, snap-through instability has been used for a fast locomotion and also for a high-speed catching. So now, what are the advantages of introducing this type of mechanical instability into these devices? So we're basically able in this way to address some of the main challenges in the field of soft robotics. So one of that is for sure the power amplification, right? So we know that soft robots have the tendency of a low power output, and we can amplify that by harnessing mechanical instabilities. We can increase in this way also the actuation speed. So we know that the speed of actuation in soft machine is very limited. And this is due to the intrinsically kind of rate of deformation that is low and the elastic recovery of typical of compliant bodies. So we can also simplify control strategies. So in the previous talks, we have seen also how control strategies can be challenging in soft robots. And we can also embed sequencing capabilities in a very pre-programmable fashion. So today I would like to briefly go over with you two projects we have ongoing in the lab. So the first one is a bio-inspired buckling-induced distributed gripper, and the second one is on how we can achieve transition waves, so transmit a signal in a nonlinear mechanical metamaterial. So let's get started with the first one. So something you might not know about marine sponges is that they are the most ancient animal on Earth. They are known for not having a nervous system. However, what they can do, they have sensory organs that allow them to sneeze, okay? So we see how the sneezing mechanism looks like in this phylum Porifera, where we have kind of an expansion and a contraction of the overall body. And this, from an engineering standpoint, so looks like it's been actuated like it's in inflation and then a deflation, consequently, in this alternative motion. So what we try to replicate in the lab has been a cellular elastomeric metamaterial with a fluidic actuation. So as you see, the input is extremely simple. So it's just one channel that is inflating and deflating an internal cavity of this 3D cellular structure. And what we observed that both upon inflation and deflation, we reach a buckling instability that is going to rearrange the patterns and it's going to cause a cascade effect of buckling within the material. So what we want to be able to do is to predict when this type of phenomena are going to happen within our metastructure. For this reason, we developed a finite element model where we can replicate what is the pressure volume response, and we identify what is the onset of this buckling instability where we have a sharp change in slope. And we see we are in good agreement with an experiment and the finite element case. Now, what we also modeled then is what are the instability modes? So how are they going to look like? How is our metastructure actually going to deform? And we see that upon inflation, we get this diamond pattern shape, while upon deflation, we get the more standard alternating ellipses trend. So you might be wondering, what can we use this for, right? So it's very intriguing. And our idea is then to use all this for having a distributed gripper. So in this sense, we are increasing the pressure inside our body, and the pores are going to all collapse. In this way, we can pick up and grasp strands or flagella that are very thin and slender. And by applying distributed load, we are not going to reach the threshold for tearing one single flagella. And then once we release it, we reduce the pressure, we're going to see our artificial algae that is just going to sit back in our tank. So to move on a bit to the next project, I would like then to talk about transition waves. So to talk about transition waves in the linear mechanical metamaterials, we need to introduce the concept of multistability. So multistability means that the system has multiple stable configurations. Now, multistability has shown that can be used to achieve transition waves, both in 1D systems and in 2D systems. So what do all these design have in common? So they have in common the fact that the building blocks, so each element that you're seeing transitioning from one stable state to the next stable state, has an asymmetric energy landscape. And what do I mean by that? I mean that we set the element in its higher energy walls, and when an input is received, this transition to the lower energy walls. And this causes a cascade effect within the 1D or the 2D chain. So now, what is the issue with this type of approach? So the issue is that this is not a reversible signal, because once we end up in the lower energy walls, we cannot send a second signal right after. We will need to manually recharge each element. And what if we want to overcome this limitation? So we want to be able to send multiple signals, and we want to be able in this way then to encode and encrypt a language into this. So one strategy we thought about has been to have a symmetric element with symmetric array. So what I mean by that, symmetric element, it means both the stable states correspond to the same energy, and we are patterning them, so one after the other one, in a symmetric fashion. So what is the simplest bistable element we can think of in mechanics? So it's a buckled beam. So what we do, we take a beam, we compress it with an axial load, and then we set it, so we fix it in its buckled state. So both upward and downward configurations are equivalent from an energy standpoint. So the beam can either stay up or down. Now, what if we use this as a building block and we actually allow multiple elements, one after the other one, to be connected and react to the signal? So what we are seeing is that by actuating one element, we are transmitting the signal in the change from left to right, up to down, but also from right to left, up to down, right to left, down to up. So the system, in this way, we have reversibility and also reciprocity. So it's the same signal going from left. Now, what is the limitation with this approach? Is that there is damping in our system. So when we keep adding element, the signal eventually is going to stop. So damping is preventing the signal to travel, so from traveling over arbitrary distances. So then we start thinking, okay, how can we predict this type of behavior? So if we're able to predict it, we can also come up with new strategies to overcome this limitation. So for this reason, we developed a theoretical model. So we started with our chain of arches, and then we went to the building block level. So each arch has been treated separately, and then we introduce what are the boundary conditions that allow them to talk to each other. So there is going to be a continuity of the rotation, there is going to be a moment exchange, and then thanks to that, we can write the single element equation of motion. And as you see, is a PDE, so it's a partial differential equation, but by using a series of sine functions that is a complete base for the system, and we can stop to considering 3 modes for replicating our dynamic response. In this way, we can easily then integrate our system and find the temporal response. So if we look at what is our agreement so between the experiment and the analytical model, we see that we can capture very well what is the overall dynamic of the system. So again, we are indenting the first element. At the bottom, you see how the midpoint is moving with respect to time. And we capture so this traveling wave going through the material. So once we have this, powerful numerical analytical tool, we say, okay, now we can start getting more creative. So remember, we had the issue that our signal was stopping after a certain number of elements because of dissipation. So now what if we put symmetric element, but this time we introduce an asymmetric array. So as you notice, each element has symmetric energy wells, but if you look at the energy barrier, so at the jump that we need to do in order to go to the new stable configuration is graded. So it's gradually decreasing in the chain. So this means that we're putting one arch after the other one with a lower rise. So in this way, the energy required for the snapping is going to be less, one element after the other one. So in this way, what we can create is a reversible mechanical diode. So if we actuate our system from left to right, we would see that we have a signal propagating within the medium. Now, can we redo it? So again, from left to right, but this time from down to up. And yes, the answer is we can redo it without the need of manually recharging the system. So as you can see, this can be done multiple times, and we can increase obviously the length of our system as well. Now, in order to prove that this is an actual diode, we need to show that if we indent our system from right to left, there is no signal propagating within the system. And this is exactly what we see. Same if we do it from down to up or from up to down. So another interesting arrangement that we can play with is by alternating symmetric and asymmetric elements within this array. So since the arch is a very simple element and they can be patterned very easily, we can think of having a bistable element with asymmetric energy wells and then a bistable element with a non-symmetric energy wells. So how do we make the element with the asymmetric energy wells? So the way we do it is that we plastically deform it in a way that we have already done the form state in which with the arch is already an arch. So it's not a beam anymore, but it's plastically deforming one configuration. And then we set it in its higher energy world. And we insert this in our chain. Okay, so it's a very simple trick, but it works very nicely as a battery element because we are in this way storing more energy within our system. So then we can play, as I was saying, with the pattern. So here, for instance, we have 2 elastic elements that are buckled beams and 1 plastic element. That is the violet one. So now what we want to show is that we are able to send a signal from the left to right. So the arrows identify the battery element. And then we can also send a signal from the right to left configuration. And this is what we actually show here. Now, you will notice that the signal they were sending from left to right and the one we're sending from right to left, they are different. They are because actually the arrangement is non-symmetric. And the last element, as we see, is a buckle beam, and then we have a plastically deformed element. But on the left, we have two buckle beams. So we get into a situation on the right-hand side where the signal starts way earlier with respect to what we have in the left. So we are basically encoding and encrypting non-reciprocity into a system in a passive fashion, right? So it's just by playing with the tessellation and the energy wells of each element. So to conclude, so you might think, okay, what can we use this for? So again, the fast actuation and the sequencing are the main skills and then the main pros of these systems. So we can actually accurately calculate what is the initial velocity that we impose at each bolt in this cannon and in this chain reaction effect. So and this simplifies all these also control strategies. So with that, I would like to thank my students, so Midun Varghese and Anthony Jones, for working on the bio-inspired vacuum-induced distributed creeper. And for the transition way further, I would like to thank my collaborators, Professor Bertoldi at Harvard University and Gabriele. And I would like to thank you for your attention, and I'm happy to take any questions.
Awesome. Thanks a lot. This was a very interesting talk.
Thank you.
There's a question here from Swaroop Kumar asking, is this system operated in a range before further bifurcation happens? And there's, I think, a second question sort of, is chaos considered in this study?
Okay, I don't know if it's referring, okay, I'm assuming it's referring to the second system maybe, or well, bifurcation is in the buckling. We have the first instability that is a sort of bifurcation because it's a buckling that we see in the sponge. And for the transition wave, now we have the snap through instability, and this is the first bifurcation. Now we also did a study that is we published in PRE last year. Is on the single element, so on the arch itself, and that so we investigated the type of instability, how it's originated, how it's triggered, and because as you see, there is an activation of an asymmetric mode, and this causes a loss, so a drop in force, and after that we get the snapping. So yes, this is a deterministic system the way we studied, because we also studied the indenter, how much the speed of indentation is affecting the response. So there are many parameters to play with into the system. Actually, what we observe is that in a chain, the velocity or the propagation of the signal is independent from the velocity of the speed of actuation. And this is a very interesting feature of a system because they are uncoupled. So, and it's something, again, we can pre-program. So we can decide if we want a system in which a signal is going to travel at that speed over that distance. So we can very well localize what the response is going to be in a predictable.
Awesome. Yeah, this is great. There's another question, but maybe you can take it after the talk. But I would like to thank you again for an excellent talk on behalf of everyone.